In this next example, we're going to look at the cost to bury a cable if running a line to a house. And so, considering this situation like a cable company or an electric company has to bury a cable, the junction box is located 5 miles down from an intersection, and the house is 2 miles down from the intersection at a 90-degree angle. And so basically the idea here is you have the potential to just run a cable underground from the house directly to that junction box. That would be one option, but that unfortunately maximizes the amount of distance that you have to bury the cable, which is an additional cost to the company. Or they could run that cable above ground, just string up telephone poles and run cables down the road. Now they could do that, and they could just bring that cable straight down to the intersection and then run it across. The problem with doing that is you've maximized the total distance now. So you have a total of 7 miles to cover to reach the junction box. And so somewhere in between there's got to be a happy medium where you minimize the total cost, because as I have written up here, the cost to bury the cable underground is $700 per mile, and the cost to run the cable above ground is $500 per mile. So it's definitely cheaper to run it above ground than it is to bury it underground. However, you want to avoid this longest distance, I suppose, if that cost ends up still being more, even though it's still above ground. So the trick here is to determine a function, to write the cost as a function based upon where the turning point is. And so you may find that running the cable above ground for a portion of that distance and then underground the rest of the way may be the best way to minimize cost. And so the idea here is to find the point at which that turn would take place. So here it says build a function c of x that expresses the cost, that's your c, as a function of how far above ground the cable is run. Well, the cable is run above ground from this junction box over. We don't know yet how far, but we're going to call that x. Okay, that's our input. So this distance here would be x. All right, that's how far the cable would be run above ground. Now that could be moved all the way over to this corner, or it could be, right up next to the junction box. I'm not sure. We'll find out. So you're going to run the cable above ground up to that point, and then you're going to run it underground or bury it from there to the house. Okay, and so we need to figure out these two values. Okay, so first of all, we can figure out the cost for each of these based upon the distance, right? We know the cost is $700 per mile above underground and $500 per mile above ground. And so if I want the cost, I just take the distance times the rate, and that will give me the total cost. So what I really need are the distances. The first distance is x. Well, the above ground cost, right? Or the above ground distance. So above ground is going to be, above ground distance is x. So the above ground cost, let's make that a little g. Would just be, let's say, the $500 times x, right? So it's $500 per mile, 500 times x would be the total cost. Okay. Now below ground, the distance is found using the Pythagorean Theorem, right? This is a distance formula kind of problem because we're going on a diagonal here. So let's use a different color for that. So below ground, or I'll say underground, I should say. Underground distance. Well, we need to use a Pythagorean theorem on this triangle. The two sides of a triangle, one of them is 2 miles, the other one is this number here that we don't know. But we know that if I add this plus x, I get 5. So that must mean that 5 minus the x gives us this remaining distance. Right? So here we have 5 minus x. That's the distance from the intersection over to where the cable turns in underground. So the sides of the triangle, if you were just to separate that triangle off, you would see that the underground distance is found using the two legs, 2 miles and 5 minus x. So we could use the Pythagorean theorem. We take the square of each of those legs, add them together, and take the square root. So the distance is the square root of 2 squared plus 5 minus x squared. That would be our distance. I could simplify that a little bit. Let's call that 4 plus, well, 5 minus x all squared. If you do 5 minus x times 5 minus x and distribute, it's a perfect square trinomial. It would be 25 minus 10x. You double their product and then add the square of the last term. Okay, so square the first term, square the last term on the ends, and then in the middle it's double their product. And then I could simplify this one step further, and I would have the square root of x squared minus 10x plus 29. Okay? So that's a distance equation, but that doesn't give us the cost. So that's our underground distance. The underground cost is going to be found by taking this distance and multiplying by the $700. Right? So it's going to be 700 times the square root of x squared minus 10x plus 29. Okay. So now the question asks to build a function c of x that expresses the cost as a function. So this is the total cost, right? Not just the individual cost. So now I need to add these two costs together to get my overall cost, right? The underground or the above ground cost and the underground cost added up will give me the total cost. Okay, so I'm going to erase a little bit of this so that I have some room to work. Okay, and so in the end, we want our total cost, c of x, to equal 500x plus 700 times this root, which is x squared minus 10x plus 29. All right, that should do. There's our function. Now we can do a lot with that function. We could figure out how much it's going to cost. If that line is run 1 mile above ground, or 2 miles above ground, or 3 miles above ground, we could try all those and see, what we get out. So we could see if x is 1, if we're running it 1 mile above ground, then we could figure out what the total cost is. It'd be 500, right? The x becomes 1. 700 times the square root of, this would be 1 minus 10 plus 29, which would equal, let's see, 500 plus 700 times the square root of 1 minus 10 is negative 9 plus 29 is 20, right? So it'd be a square root of 20. And then, of course, you could just evaluate that and get a pretty close approximation on your calculator. 500 plus 700, oops, what happened there? 700 square root of 2, and, oh, sorry, nope, square root of 20. What am I doing? There we go. That gives me a value of about 3,000. Oops, I should put a $sign in there. So that is $3,630.50 if I round that, 49.5 cents. Okay, so that would be the cost to run that 1 mile underground and then straight over to the house. Or I'm sorry, 1 mile above ground and then straight over to the house. Okay, if I wanted to do that, let's say we ran the cable, 4 miles over and then turn it in toward the house. Oh, we can just plug in a 4 instead of a 1 and do the same sort of thing. These values will all change. Those values change. The 500 changes. Okay, so if I ran that 4 miles, 500 times 4 is 2,000. Let's see, 4 squared is 16. 10 times 4 is 40. And add 29. So let's see, what would that be? 29 minus 40 is negative 11. Plus 16 would be 5. So that would be 2,000 plus 700 square root of 5. And if I plug that in, 2,000 plus 700 root 5, I get about, that's a little bit less. This one would be $3,565.25. Okay, so it looks like it's maybe about 65 bucks less. Okay, so slightly cheaper doing it that way. Now the question is, the real big question to me is, where is that cost minimized? Can we minimize the cost or find the value at which that cost is least? And again, using our calculator, we can do that. If I go to my y equals screen, right, go to the y equals screen, you can insert this function that we created. So 500x plus 700 square root x squared minus 10x, oops, typoed, okay, 10x, plus 29. And I'm going to hit enter. Alright, so there's my function. Now you can't see the whole thing, but it's in there. And then I'm going to go to, well, I got to zoom this somehow. I already know that my outputs are going to be, fairly large numbers in the thousands here. So I don't want to just go to my standard window. I know that the inputs, the x values, can only range from 0 to 5, right? 5 is this total distance, so I can't go more than 5. That wouldn't make any sense. So I'm going to go to my window, and my x values, I'm going to go from 0 to 5. And my y values, I know I've got to get all the way up at least to 4,000, right? Got to get up above that number. Maybe a little higher than that. Let's go 4,500. Let's go 0 to 4,500. And I need a scale. I need a scale that's kind of reasonable. Let's do like a 500 scale maybe. That would give me 9 tick marks. Right, so something like that would be a decent window, I think. Let's hit graph. And there it is. Okay, so it definitely goes down and then comes back up. So there is a minimum in here somewhere. So our goal is to find that minimum. Okay, so I'm going to go to my calculate menu, as we've done many times now. Go down to the minimum. We'll do our normal left bound. So go left of that minimum. Then I go to the right bound. And then we give it a guess. So put that cursor somewhere in between. And there's our value. It appears to be about 2 point, I don't know if that's going to focus, 2.96 roughly, 2.96 miles down. Okay, so that would give us our optimal cost. Let me erase some of this. Okay, so the optimal cost there, the minimum cost occurs at x approximately 2.96 miles. So that would be almost 3 miles down the road when you turn in to go to the house. So that's the minimum cost. And the min cost is, according to this, right around $3,479. $3,479, and if I round that off, that's 80 cents. Okay, so that gives you an idea then of what the minimum cost is, where the minimum cost occurs. In this case, it's optimized at almost 3 miles down the road. So running that above ground for 2.96 miles and then burying the cable underground gives you the minimum cost for this scenario. Okay. Now, of course, if I change the original cost of the original rates of 500, 700, if those change, then that would change where this is. It doesn't change our function, just changes those two numbers. That's all it would really do. The derivation of the formula would be the same, but it would change definitely where this mileage changes, or where it turns in, and it would also change the minimum cost. But it gives you an idea of how to set up a problem like that. There are many other types of problems like this. Imagine if you were trying to get to shore if you were off in a boat, you were trying to get to shore, but you were trying to get to a particular point downshore. The question, obviously you're going to be traveling slower in the water than you would walking along the land. But would you go straight to the point that your destination on an angle, or would you go to land and then along the land, or would you find a happy medium in there somewhere to aim for before turning? And so your rate of speed can affect the overall time it takes. And so it'd be a similar situation to this, using a rate of speed rather than a rate of cost. Okay, so lots of different things that we could use a similar scenario for. But in this one, I think it's kind of neat just to see how you can find that minimum cost, or how you can optimize that value.